Okay. To do this integral from 2 to 4 of 6x dx, take the 6 out front, which you can do. You can take constants out front. Okay. We'll end up with x dx. They told you that the integral of x dx from 2 to 4 is 6, so this is 6 times 6. That would be 36. I think that's what they want you to do. Okay? Just do it that way. Of course, you could just do the integral of 6x dx, which is 6x squared over 2, 3x squared from 2 to 4. Here, you could do it this way. Do this definite integral. That's 6x squared over 2. That's using our rule for x to the n form. From 2 to 4. That's 3x squared. That's correct. From 2 to 4. And what we said, what you do here is substitute in the 4 to get 16, 4 squared. Substitute in the 2, 2 squared. And that's equal to 3 times 16 minus 4, 12 times 3 is also 36. But what they wanted you to use is these 3 things here that they gave you. Okay, but either way works. Okay, we did this at the end of the class. We did a limit. We did this big limit thing. And I said, okay, instead of doing this big limit thing, we can use a definite integral. That definite integral takes takes the place of that whole limit process. Okay? So we established that last week. We had this limit, okay, of a sum, of an infinite sum, and that was equal to that integral. And I want to make that proof. That's the proof I want to do today. Okay, she's got another question on here, number 8.
So I asked one of the other one I can figure out.
Oh, okay.
They're the same.
Yes, they are. Basically, they are the same.
Where did the 60 come from? Was that part of the problem?
Where it come from?
The 60.
The 60 came from, yeah, they gave you that. They gave you this, they gave you this, they gave you this. And then they asked for this. And then what they wanted you to do is use these, one of these, some of these. I don't know why they gave you all 3 of them, just for laughs, I guess. And they wanted you to use these values to evaluate this integral. And that's what we did. Oh, but we also did it this way, too.
It was a good joke.
Yeah. Yeah. You have a sense of humor when you're doing these things.
Yeah.
Okay, any other questions? All set?
Let's hit the road.
Let's go. Hey, let's do some proofs. Let's do some stuff.
Are you going to use a pen or?
I don't know.
It's running out. The marker's running out.
Is it?
Where's that lucky pen of yours?
This is my. Let's see. As long as you can read it.
Well, we read it.
Wow, it looks really all right. As long as you can read it. What we're going to do here first is called the mean value theorem. Okay. For integrals. That's the first thing we're going to do. We're going to do 2 proofs here. Okay. Mean value theorem for integrals. Now recall. What do you think, Jeff? You that all right?
Yeah, I can read it.
Chester?
Really, I'm having a hard time seeing it for me.
I can read it.
Okay, I'll try to read it.
No, but I have I wear glasses. So it's my fault.
Oh, you wear glasses
So I shouldn't.
to see.
Yeah.
So, but you don't have them tonight. Did you drive here?
Yeah. They said I don't need them, but they should have said I did. I can read the
Okay.
I can see big things.
Oh, good. So a big person walking in front of you, you couldn't see. Well, maybe a kid you couldn't see and you just run over. I see.
She thought it was a.
What did they say? Yeah, maybe you should wear them, Daniel. I mean.
I wore them today.
Oh, good. Okay, I'm glad you did. All right. Okay, I'll write bigger. Okay, mean value theorem for integrals. Recall the mean value theorem that you have back in Calc 1. Back in Calc 1, you had a mean value theorem, okay? And usually you prove it. We proved it in Calc 1, all right? The mean value theorem in Calc 1.
What's the average?
Remember that one? the mean value theorem was this. This was back in Calc 1. You have a function of x. Okay, you have an interval from a to b. And this function was continuous and differentiable on the interval. In other words, there was no breaks in that curve. The derivative existed. Does anybody remember what the mean value theorem said back in Calc 1?
It had something to do with the tangent line, no?
Yes, it does. Yes, it did.
Equals a squared plus b squared? No.
Well,
F of c.
yes?
F prime of c equals f b minus f a over b minus a. Whoa, that was it.
I'll tell you. Damien he's out there. You haven't seen him yet this semester, but he's out there. He's out there. Here we go. What it said is that in this interval somewhere there exists a c where f prime of c, the slope of the tangent line, okay, where f prime of c is equal to f of b minus f of a over b minus a, where the slope of the tangent line is equal to the slope of this chord. Okay? The slope of this chord here connecting these 2 points is f of b minus f of a over b minus a. It's the change in y over the change in x. And it says somewhere in here there's a c where the derivative is equal to that slope. Okay? Somewhere the instantaneous velocity is equal to the average velocity. That's what it said. Well, we're going to do something a little bit different. We're going to do this mean value theorem for integrals. So let's do that. We're going to be given f of x, continuous, and differentiable. And you're not going to be responsible for the proof, obviously. I'm not going to ask you to do a proof or something like that on the test. But what I do want you to do is see if you can follow it and understand it. Okay, that's what I'm after. Okay? Continuous and differentiable on some interval from a to b. Then, there exists a c in the interval such that the area from a to b is equal to f of c times b minus a. What the heck is that? Okay, let's take a look at
What's
this.
differential?
What's the what?
Differential.
Means the derivatives exist.
Oh.
In other words, you don't have any spiky curves like this. Okay, where do derivatives not exist? Derivatives don't exist where you have gaps in a curve, but we don't have any gaps because we have a continuous function. But where the derivative does not exist would be at a spike like this. The derivative doesn't exist at that point. That's a cusp point.
Okay.
Derivative doesn't exist there. So we're talking about functions that are continuous. What's a continuous function? Continuous function from here to here takes on all the values in between, doesn't skip any values, there's no breaks in the curve. It doesn't go up like this, and then start down here and come up again. That's discontinuous, okay? Continuous function has no breaks in the curve. If the continuous function is negative here and positive here, and it's continuous, what can you tell me about that function? What other value must it contain?
0.
It must be a 0 somewhere in between. Okay? It's got to be. Okay? That's a continuous function. So, here's what yes, Danielle.
What's the weird looking triangle thing? Maybe?
What?
That's an A. There's an A.
This
I
here?
wasn't making fun of
Is
you.
that a
Right.
triangle or
That
a?
was just
That's an A. That's the area from A to B.
Oh.
That's the area from A to B. Okay? Here's what I'm saying. I'm saying this. I'm gonna get a bigger diagram. I'm saying this.
Everybody got that?
She's still ready. You all set? Okay. I'm saying this. Here's their function. Okay, from A to B. I'm saying somewhere in this interval, from A to B, there's a C value. Where the area under this curve, the area from A to B, is equal
You're
to.
not on the screen.
I'm off the list, or I'm off
You're
the
off.
thing? I'm off the thing. All right. I thought I had it. Oh, for Pete's sake. Okay.
Awesome.
Okay. Where the area from A to B is equal to f of C. Now let's see. What the heck is that? This is, bless you.
Thank you.
F of C is this height times B minus A, which is this length here. What it's saying is, somewhere in this interval, there's a C, where the area under the curve from here to here is exactly equal to the area of this rectangle. Okay? That's what it's saying. F of C times B minus A. Okay? That value, F of C, is called the average value of the function.
Now, is f of c on the mean point?
No, it doesn't have to be right in the middle. It would be right in the middle if my function were a linear function. If this were linear, then C would be right in here, because this excess area would equal this deficient area over here. It would be right in the middle. But if I've got some function that's doing something like this, it may not be in the middle. It may be way over one side or way over the other side, depending on the function.
No, but I'm saying is that then where c is that where we're looking for the mean value?
We're looking for where that C would be, and that is called the average value.
Okay, that's
Yes, the
what-
mean
that's
value,
what I
yeah.
was-
Okay, let's take a look at this. Let's take a look at the minimum value. Let's say this is the minimum value of the function. And the way I've got it, it looks like this. Well, I'm going to call this the maximum. All right? The function's going to have a minimum or a max and a maximum on this closed interval.
Does the maximum have to be on the line or no?
No, it doesn't have to be. It could be. You could have a function like this. The maximum could be here.
So technically it's, where's the box sense, no?
And the way I've drawn it, the maximum is here. But I could have a function, if my function looked like this, and here's, let's say this is A, and this is B, like the minimum could be like here, there's the minimum, but here would be the maximum. Okay? If a function's continuous on a closed interval, it's another Calc 1 thing, it's guaranteed to have a minimum value and a maximum value. Okay? That's guaranteed. Where do those minimums and maximums exist? When you in Calc 1 and you're looking to minimize a function or maximize a function, where do you look for minimums and maximums?
Would it be the first derivative?
Yes, you set the first derivative equal to 0 at critical values. There's one place. Where else is it possible to have a minimum or maximum? Endpoints, okay? Endpoints is the second point. That's guaranteed. If you've got a continuous function, it's on a closed interval, that is, includes the endpoints, it's guaranteed to have a minimum and a maximum. Where will those minimums and maximums exist? Either at critical values, first derivative equal to 0, or at endpoints. Guaranteed, okay? That's Calc 1 stuff. All right, so here's what we got. This area from A to B is going to be greater than or equal to the minimum value of the function times B minus A, but less than or equal to the maximum value of this function times B minus A. It's got to, okay? All right. When would these two be equal to each other? When will these be equalities? What kind of function must we have in order to get equalities here?
Where they have min and max are the same?
Yes, that's true. And what kind of a function would that be?
Oh, vertical.
What's that?
I don't want to be wrong. Horizontal line.
You're perfectly right.
Okay.
Horizontal
Oh, I
line.
got it wrong.
You got a constant function, minimum, maximum, the same. Yes, indeed. The area under that curve is equal to the minimum times the value of the function everywhere, because it's all the same, and the same with the maximum. But generally speaking, the area under that curve is going to be greater than the minimum times the width, but less than the maximum times the width. Does that make sense? Makes sense? Good enough? No. Okay. Let's suppose, let me give us some values here. Let's suppose this is like 0, 8. And let's suppose this value is like, A8. And this is the value of B20. Okay? Something like that. The area under the curve, this area under here, is going to be greater than 8 times this width. Now, 8 times this width will give me the area of this rectangle. Okay. Here. It's going to be greater than that, but it's going to be less than this area of that rectangle, the biggest rectangle. It's somewhere in between the two. Okay? And that's what I'm saying. It's going to be somewhere in between. And the only time it's going to be equal to both is when we have a horizontal line, a constant function. Okay, I'm going to divide both sides by b minus a. So the minimum value, okay.
Is this the proof?
Yes, this is a proof of the mean value theorem for areas, okay, for integrals.
The b minus a, is it the x values or the y values?
b minus a is this width right here.
So it's the x values?
Yes.
Okay.
Yep. So what I did, I divided this inequality by b minus a. Now here's what we have. We have the area of this function over b minus a. We have some number here that's between the minimum and maximum. But this is a continuous function, our function f of x, meaning what? It takes on all values from the minimum to the maximum. That's what it means to be continuous. It doesn't skip any value. Therefore, because this is a continuous function that we're talking about, there exists a c in the interval as an element of this interval. Okay, this is a c in here somewhere, where the function, value of the function, is equal to this number right here because it's between the minimum and maximum.
So all you did was take out f of c, pretty much?
Yeah, all I'm saying is somewhere in here I know there's a value where the value of the function is equal to this number because this number is between the minimum and the maximum. And the function takes on all the values. So there is some value in there that f of c is equal to this. Then what? Multiplied by b minus a. So the area from a to b is equal to f of c times b minus a. Okay?
That's the whole proof?
That's the whole proof, QED. That's the proof of the mean value theorem for integrals. What it says is somewhere in there there's a c where the area under the curve is equal to the value of the function at that c times b minus a being the width of this rectangle. That makes sense, right? I mean, if you started here at the minimum, it's too small, this rectangle. And then as you go this way, the rectangle gets bigger and bigger. At some point, the area of the rectangle is exactly equal to the area under the curve. That's what it's saying. All right.
As you go higher.
Yes. Yeah.
Can we prove the proof?
No, we did the proof. The proof is the proof.
No, can we prove it with numbers?
Oh, well, yeah. Actually, that's going to be on your test too. I think I have at least a couple of them there where I ask you for this average value thing. Yeah, let's do one right now. Let's do one right now. Let's take a function. Let's take f of x equals x squared. Let's take an interval from 0 to 4.
What's the function again? Because there's the record button on it. Okay.
What happened? Oh, x squared.
Okay.
Yeah, I do that sometimes.
At least the record button's smaller this time.
Yeah, before.
Remember how big that
Yeah,
was?
the other one was like a quarter of the page. All right, this would be a 416. Okay? Here's what we're looking for. Let's find that C value in this interval where the area under the curve, the area from A to B, 0 to 4, okay, is equal to the value of the function at this C value. Okay? Well, let's take a look here. The C value will be in here somewhere. Okay. So how do we find this C? Well, f of C is going to equal, just what we did, the area divided by B minus A. How do you find the area under this curve? Well, we have a couple ways of doing it. Well, one way we have of doing it is setting up an infinite sum. We could divide this into little rectangles. And we could sum up all those little rectangles, and we could let the number of rectangles go to infinity. Believe it or not, that's what we did last week. We took y equals x squared from 0 to 1. We divided up into 2 rectangles, then 4 rectangles, then n rectangles, and then we let n go to infinity. And we found the sum, that limit as n goes to infinity of that sum. And we found the area under the curve that way. Okay, it took a while. And then what I said was, instead of doing that, what you could do instead is do an integral of the function from 0 to 1, and it's instantaneous. It came out to 1/3, the same thing we got from the limits. Okay? What's the area of this from 0 to 4? It's the integral from 0 to 4 of our function dx. That's what this value of C is. What's the integral of x squared? What's the antiderivative of x squared? What's the function whose derivative is x squared? X cubed over 3 from 0 to 4. This is called the antiderivative of x squared. Oh, you haven't done anything on this?
I wanted to do it today, and then I didn't have the code,
Oh,
so I
yeah.
gave up.
Okay. Yeah, you are behind some. Can you get here during the day at all?
Yeah.
You know, that may be a useful thing, if you can get here during the day.
This is only the third class.
I know,
Still,
but missed so much. I know.
And one of the classes is online already, so.
Yeah, see, we got the first one is not online, but the second one is online, and the third one is
Right there.
now. Is this our third class? Serious?
Yeah.
Wow.
I know. She makes the formulas really. That's the thing. That's what the first class was.
Yeah. All right.
They don't want me to come during the day. They really don't want me to.
Who doesn't?
All of them, they're like, just do that line.
No.
I think
They want to make it easy for you.
formulas.
Yeah, they want to make it easier for you. I have the notes too written out. I have all the notes written out too. I'll just give them to you after class. Maybe I can, we can kind of go over them a little bit so you know what the heck. Or maybe you could take them, look at them, and see if you can make sense out of them. And if you can't, then the thing to do would be to maybe come in during the day, and we can go over them or something like that. All right? Well, we'll get it. You're a bright person. You can do it. Okay. Anyhow, this is called the antiderivative or the integral of x squared. Why? Because its derivative is x squared. That's what this notation means. This integration symbol with the dx together say, find that function whose derivative is x squared. And we have a rule for it. The rule is the integral of x to the n is x to the n plus 1 divided by n plus 1. Okay. Plus a constant. Okay. This is called the integral or antiderivative of x to the n. Why? Because the derivative of this is equal to this. You got to be careful here that n can't be -1. We got a division by 0, so it doesn't work for that. We need something special for that. But we have rules. We have about 6. We did about 6 of them. x to the n, we did e to the x, we did a sine x, we did a cosine x. We probably did secant squared as well, because that's integral as tangent. I think we did secant squared as well. We did about 6 of them. And they must be in the notes, so I can give you the notes. Okay? Okay, let's substitute in. 64 thirds. Okay. Minus, substitute in the 4, substitute in the 0. This gives you 64 thirds divided by 4. That gives you 64 twelfths, which we can simplify to divide by 4. Okay, we'll get 16 thirds.
How did you get the 0?
Substitute in 0.
Oh, you substitute in 0.
Yep. Okay. We get f of c is 16 thirds. Now, what is the 16 thirds? That's this height right here. That's the average value of this function. That height, it's the height of this rectangle whose area is exactly equal to the area under this curve. Okay? That's the height of that rectangle whose area is the area under the curve. It's called the average value of the function. Now, of course, Compass is going to ask you for that, but they'll also ask you, what is the c value that gives us this value of 16 thirds? What do you have to do there?
Plug it in, right?
Yeah, that's it. That's exactly right. Here's our function. Okay, we want to know what c value gives us 16 thirds. So x squared has to equal 16 thirds. Take the square root of both sides. So x is equal to, now we've got 2 values, but we only are concerned about 1. The square root of this, which would be 4 over square root of 3. Okay, and you could rationalize it. 4 square roots of 3 over 3, let's say. Okay, that is this point right here. Okay. Everybody see that okay? Okay. That's the c value. This is the f of c. It's the f of c that's the average value of the function. Now, if you're a computer programmer, okay, you want to test the randomness of your the random number generator that's built into your operating system, into your programming language. What you could do is something like this. Take a function x squared, take an interval, say, from 0 to 4. Let's take 1,000,000 values at random from 0 to 4. Take about 1,000,000 values. Take their squares. Add up all those squares, 1,000,000 of them, and then divide the total by 1,000,000. What should you get for an answer after doing that?
Something called
Something very close to 16 thirds. That's what the average value of a function will give you. Okay? 16 thirds.
I have a question.
Yes?
Is there any formula that does it straightforward, finds the area under it without using a rectangle, like rectangles?
Well, the area under the curve is the integral.
Oh, is the integral?
Yeah, the integral gives you the area under the curve. To get the average value, though, this is the kind of thing you're going to have. Here's the formula for average value. You ready for this? Go ahead.
I'm still a little confused.
What's that?
64 to 30. If you plugged in 0 for the x, wouldn't that give you? That won't give you 6. Or you plug in the 4 for the x.
4 for the x,
Oh, okay.
and then the 0, and you take their difference.
Oh, okay, that makes sense.
Okay, no problem. Here's the formula for average value. I wasn't going to quite do it then, but we can do it right now. Here's what you got. Average value of a function is 1 over b minus a, the integral from a to b, okay, of the function dx. That's how you find the average value of the function. And please note, that's what we just did. Okay? When we did this right here, that's what we did. We did the integral over b minus a. That's what this is. Okay? That's the average value. Now, does that have any practical use?
Probably.
Yeah, it does. if you have a alternating current travels in a sine wave, okay, like this. There's something called the effective voltage of an alternating current. And the effective voltage of an alternating current is the average value over that sine wave. That's what it's called, the effective voltage. Yeah, we can do it. The effective voltage is equal to, here's what we're going to do. We're going to take one branch here of this sine wave from 0 to pi. The effective voltage of an alternating current is equal to 1 over b minus a, pi, the integral from 0 to pi sine x dx. Okay? It's called the effective voltage. That's 1 over pi. What's the integral of sine?
Minus cosine.
Negative cosine, opposite of cosine. Okay. Substitute in pi. What's the cosine of pi?
What's the what?
What's the cosine of pi radians?
Pi radians?
Cosine of pi. I don't think I've heard it yet. Negative 1. Thank you, Gessner. It's negative 1, but we have to take the opposite of it, so we do get a 1 there. Minus, plus, cosine of 0. What's the cosine of 0?
Cosine of 0 is 0? No, it's 1.
1. We get 2 over pi. And in circuits, 2 over pi is called the effective voltage of an alternating current. Okay? 2 over pi, whatever number that comes out to be. All right? So that's one application of that average value. Go ahead.
Can we just review it a little bit? Sorry.
That's all right. What I'm saying is the effective voltage is that height of that rectangle right here, whose area is the exact area under this curve. That's called the effective voltage. And you find it by taking 1 over b minus a. Now this is your b, this is your a.
Oh, okay.
The integral from a to b of the sine function. Okay? Because that's what a current is, sine wave. Okay?
Sine is negative cosine.
Integral of sine, negative cosine from 0 to pi. Substitute in pi. Cosine of pi is negative 1. Take the opposite of that negative 1 to get a 1. Subtract. Minus, plus. Cosine of 0, which is 1.
Okay. That makes sense.
Okay. We all set on that?
So what happens to the dx?
See, it's the notation. This together with this say find the function whose derivative is this. So we've done that. That is the function whose derivative is sine x. If you take the derivative of this negative cosine x, its derivative is sine x. Okay? These guys go together. You can't have an integration symbol here without having the dx symbol here. They go together. Okay? Okay. You guys ready? We're going to do the big one now. All right? The big one is to show that the area under the curve is indeed that integral. We already know the area under a curve is an infinite sum. It's a Riemann sum, okay, by taking that limit. Okay? You okay, Dee?
Yeah.
Oh, okay. Oh, okay. All right. What we want to show now is that that area is also equal to that integral, proving that the integral is equal to an infinite sum. We'll have these three quantities equal to each other. And we're going to take advantage of that throughout the course when we do applications of the integral. This is called, by the way, the first fundamental theorem of integral calculus. I mean, this thing is big. Okay? This is what it's called. Okay? Now, this is going to get a little mathy, okay? It's going to be a little bit mathy here. You know, we got, math majors, we got math
No,
majors.
no,
No, go ahead. What was that?
I'm not a math major.
Oh.
The one that we just did, the proof we did before,
Yep.
we were trying to prove that it's the area under the curve. What-
No, we tried to prove that there is a C value in that interval somewhere where the area is equal to the area of the rectangle.
So
And we
pretty
proved
much
there is a
the
C.
C value that equals, the C value that has an X and a Y that equals the rectangle, which equals the area under the curve.
Yes, that's
This-
it.
This is to prove that the integral is the area under the curve.
That is correct.
Okay,
That is correct.
just want to make sure.
That's correct. How we doing, all right? Trent, how you doing?
Super.
So you must be working like 20 hours a day for crying out loud.
Busy.
Yeah, wow.
It's all in physics.
You do snow plowing, right?
Yeah.
Wow, jeez.
One day.
Hey,
Paycheck.
gotta get it when you can.
Yeah,
Sleeping on bed.
yeah, there you go.
Sooner than later.
Yeah, you gotta do it. All right, I was gonna say something stupid, you know, I have a snowplow too, it was my wife. No, but, it was stupid. I forget it. Well, she likes shoveling snow. All right, all right. All right, here we go.
Are you old school?
What's old school mean?
She
Or
likes
like
shoveling snow.
using the shovel instead of using the snow blower?
Yeah, we don't even have a snow blower. But she likes getting out there and she shovels. I do shovel too.
A couple?
I do a couple.
Don't lie, you don't. He does the stairs.
Well, one stair, yeah. I do one. Well, she likes mowing the lawn too. So, what the heck?
So what, keeper?
Mowing the lawn. She likes doing that too. She's a keeper, yes, that is true. There's no question about that. Okay, here's a function. We're going from A to B. We're going to end up going from A to B, but let's first go from A to X, some X value. Okay? So, this point right here is A, f of A. This is the point X, f of X. X is some value between A and B. Okay? This here is B, f of B. Okay? What I eventually want to show with this proof is the area from A to B is the integral from A to B of our function, which is equal to the antiderivative of this f of x, which is a capital F of x, from A to B, okay, where the derivative of capital F of x is equal to, what would the derivative of this capital F of x be?
Very confusing.
I know, it is a little confusing.
Wait, antiderivative is not the integral.
Yes, it is. Yes.
Wait, so you're saying that the integral is equal to the
Yes.
antiderivative, which
Yeah.
is the same exact thing essentially, right?
Same as what thing? Well, it's easy now.
The antiderivative is the same thing as,
As the integral. Yes.
aren't they the same thing?
Yes. Yes.
So, okay,
What's the derivative of this antiderivative?
the derivative,
What is this derivative equal to?
it's derivative, no?
Yes, it is, but what is it? What I'm integrating is little f of x. We're given some function little f of x. And I'm saying the antiderivative of this, the integral of this, is some capital F of x. And now I'm asking you, what is the derivative of capital F of x?
Just the f of x.
It's little f of x, yes. That's how we know we got the right antiderivative, right?
It's like velocity.
That's what I'm saying. And how do you evaluate this? You evaluate this by substituting in B minus substitute in A. This is what we've been doing to find the area under the curve.
It's just like saying it is what it is.
Almost. You're accusing me of tautology is what that is. A tautologist statement is one that's obviously true on both sides. All right, but anyhow, this is what we're going to prove. We're going to prove that this is indeed true. Now, let's do it. I'm going to do what I can over here in this space because I hate to just take this away from you here. All right, first thing we're going to do is this. Let's see what happens as we move x over a delta x distance. I'm going to move this over a delta x. Okay, this point right here is going to be x plus delta x 0. Okay. In other words, I'm going to increment that area somewhat by a delta x. This area, okay, is the change in area from a to x. The change in area from a to x is equal to the area from x to x plus delta x. That's this area right in here. Okay? This little distance is delta x. All right? Does that make some sense? I'm saying when I move x out a little bit, I'm going to change the area. How much will I change this area? Well, I'm going to change it by whatever this area is in this little rectangle right in here.
So
Okay.
the change is equal to.
The change is equal to whatever area this is. Okay. Now, by the theorem we just did, by the mean value theorem for areas that we just did, what do we know? I know there's a c value in here somewhere. I'm telling you, this is going to get a little bit mathy. If you don't totally understand it, don't despair. It's not like you're going to absolutely need it. But I do think it's important to at least establish a connection, and hopefully it'll make some sense to you.
What does the MVT stand for?
Mean value theorem for areas. There exists a C in the interval where what's true? That this area is equal to, all right, well, can someone come up with the right-hand side of this equation? This area right here is going to equal what in terms of that C?
C would be
F of C times what?
Times x plus delta.
Nah, almost.
Would it be over?
X minus delta
B minus
x.
C.
I think you guys are right there. It's that interval, right? What's the width of that interval? That little
Delta x minus x.
delta x.
Delta x.
It's delta x. What it is x plus delta x minus x, which is delta x. That's the width of that interval right there. Okay? So, here's what I have. Does that make sense? I've got this thing here, and I know there's a C in there somewhere where the area under this piece of the curve right here, where that area right here is equal to f of C times the width delta x, which is our b minus a from before. Okay? All right. So this area from x to x plus delta x, I'm going to replace it with our delta, change in area from a to x. So here's what I have right now. The change in area. Can you still see this? Barely.
Yeah, we can.
Just barely, okay. Is equal to f of c delta x. Wow, that's exactly what I'm going to do. All right, so here's what I'm going to do. I'm going to bring this delta x over on this side. Okay, I'm going to bring it over here, and I'm going to have this.
You can probably stop recording and do widen the plane. That way you have a lot of space.
What do you want me to do?
You can stop. Hit